Welcome to our lecture video in fluid mechanics, and in this video we will solve and discuss one of the problems in one of our reference book which is authored by Gillesania, and see the description in this video for the reference. Okay. So this is the problem in chapter 3. This is problem number 3-25 under the topic plane areas. So the gate in the figure shown weighs 5 kilonewton for each meter normal to the paper. Its center of gravity is 0.5 meter from the left face and 0.6 meter from the lower face. Find H for the gate just to come up to the vertical position. So the gate that it mentions here is this member here, okay? The L-shaped member here or structure here. Okay, so that's the gate weighing 5 kilonewton for each meter normal to the paper. So the location for its weight is on its center of gravity, and in the problem it locates that center of gravity. But I have noticed a typographical error from this problem, that instead of putting here 0.5 meter, it should be 0.6 meter from the left face. Okay. So this is 0.6 meter from the left face. So that means from this member, so from there, so that is 0.6 meter. 0.6 meter and 0.6 meter above the lower face, or probably that's 0.5. There is an interchange here, so it will be, or maybe that is 0.5 or 0.6, we don't know, but the location of the weight here is 0.6 from the left face. So here is our weight. So this is W equals 5 kilonewton. And what we're looking for here is the height of the water H on this side. So H here is unknown. And what is the situation that it wants to come up with the H? It says there, find H for this gate for this gate just to come up to the vertical position. So the height of water enough for this gate to just stand erect like that. So what is the mechanism of this gate? So let's go to this bigger picture. Let's move here. So the mechanism here is that having the presence of a horizontal pressure exerted by the water here, and a pressure also exerted by the water here, being in an upright, or that is the uplift force. So if F is stronger than the uplift force here, therefore this gate will move like this, being the hinge here at this position. So if the gate opens up like this, okay, there will be enough space for the liquid to come out, or for the water to come out. So from here it will come out here. Okay. Now if the force U here is stronger than the F here, therefore it will close and stand in this position. So it will stand here in this upright position. Okay. And the stopping force is located here, exerting a downward reaction or force Okay, so these are the forces that we can see in this structure. Now let's solve for the value of H. Okay, so a while ago we were able to locate the weight being at this portion here, located 0.6 meter from the left face. So W is equal to 5 kilonewton. And then the force F here on this left side, being the water as uniformly varying, so the value for pressure increases as it goes deeper. So this is the force F. This is force F. Whereas for the uplift force here at the bottom, our representation here for the pressure of water is uniformly distributed. Okay, so that is uniformly distributed load. Let's name this as F1 here, and let's name this as F2. So F2. Okay. So first, in order to find the value of H, we need to summate or make a summation at the hinge. So here, make a summation at the hinge so as to be able to get the value of H. Now, for the location of F1, so for F1 here, for F1, this is H over 3. Right? For the location of F2, okay, that is 1.5 divided by 2. Right? So this is 1.5 divided by 2. This is 0.75. Okay. First, we need to find the value for F1. For F1, the force, hydrostatic force horizontal here is gamma of water times the HC and the area projected here. So our HC is the location from the water surface up to the center of gravity of the projected area. So this is the projected area. So this is the projected area as seen by your eyesight, side view. This is in every 1 meter. So this is H, height H. Therefore, our HC here, our HC is equal to H over 2. So F1 is 9.81. HC is H over 2 times the area. The area is 1 meter by H. So that is equal to, so F1 now is equal to 4.905 H squared. Okay, so that's for F1. Now let's go to the F2. How do we get the value of F2? Being this as the uniformly distributed load. But first, how do we get the value here? So it is gamma H. So for the magnitude of the pressure here, it's gamma H. So what can you observe from this? It's actually a rectangular prism. Right? So it's a rectangular prism. So this is exerting an upward force. So for the length of this, it is 1.5. So this is 1.5 meter by 1 meter and by gamma h for its height. The gamma h here is 9.81 h, being the gamma of the liquid, which is the water. Therefore, we now have F2 is equal to the volume of this prism. So the volume there is 1 meter by 1.5 meter by 9.81 h. So that's the volume. And that is 14.715 h for the F. Now we now have the summation of moment at 0 equals to, summation of moment at O equal to 0, being positive, say clockwise. So F1 is now positive. So the F1 here, this is the F1. This is the F2. And this is the W. So F1 is h over 3 from the hinge plus W times 0.6 minus F2. This is 1.5 divided by 2 equals 0. Okay, now let's input the value for F1. F1 is 4.905 h squared, h over 3 plus the W here is 5 kilonewton, 0.6 meter minus F2 of 14.715 h. Then the distance from the hinge, that is 0.75 equals 0. Simplifying it, that is 4.905 divided by 3, that is 1.635 h cubed plus 3 minus 14.715 times 0.75, that is 11.036 h is equal to 0. Let's arrange that. 1.635 h cubed. We will use the equation here in our calculator. If the shift solve does not work in your calculator, but you have the equation here, let's find the polynomial degree 3. So this one. Okay. So let's arrange it for that. Plus. So plus 0 h squared minus 11.036 h plus 3 is equal to 0. So what is the value of h? Now if you do the shift solve, so math, we happen to use a shift solve. 1.635 alpha x raised to 3 minus 11.036 alpha x plus 3, minus 11.036 alpha x plus 3 alpha equals 0. So shift solve. So these are the values of h1, 2.45 meters. H2 will be 0.275 meter. Then H3 is equal to negative 2.72 meter. Now if we use here the polynomial of degree 3, that will be 1.635 equals 0 equals negative 11.036 equals 3 equals. So you now have here the value for H1 as 2.45, the value for H2 as 0.275, and the value of H3 negative 2.72. Okay. So there is 3 values here. Obviously, we're not going to use the one with the negative sign. Now, which among these two, which between these two, is the answer? Now, let's go back to the condition. It says here, find the value of h for the gate to just come up to the vertical position. So, h for the gate to just, the word there is to just to come up to the vertical position. It's actually asking for the minimum value of h that could, just to come up to the vertical position. So the values that we get here is actually the limits, the h1 being the highest value of h and h2 being the lowest value. Meaning, if h is equal to 2.45, it will have this structure to stand erect. Same is true when it reaches 0.275. So it's still, the effect is that this structure will help, the height of the water will help the structure to just stand or just to come up to the vertical position. Now, for the two value, the one with the minimum there, the minimum value is the h2 here. Therefore, being the minimum, this is the answer. The minimum value of h in order for the gate to stand vertical. Okay, in order for it to close or to stand vertical. So this is the answer. Okay, so that's for problem 3-25. Now let's go to the supplementary problem 3-26. In problem 3-25, which we solved a while ago, find h when the force against the stop is a maximum. So having the force here as maximum force, find the value of h. So the highest value of h in order to exert the highest force. So how do we solve that? We have to compute for the summation of forces, summation of moment at the hinge at O, at point O. Okay? So let's have a summation of moment here. So again, summation of moment at O is equal to 0, positive clockwise. So we did that a while ago. We have there, so let's just repeat that. That is 4.905 h squared times h over 3 for the F1. So that's the F1, right? If you recall, F1 is 4.905 h squared. Then, we have to plus the weight of 5 kilonewton multiplied with 0.6. Then, minus the F2. The F2 that we got a while ago is 14.715 h. And its location is 1.5 divided by 2. And we have the additional force of P. So, the P here is positive P. And its location is 1.5 from the hinge. And then all this equal to 0. So 4.905 divided by 3, that is 1.635 h raised to 3 plus 3 minus, this one here is 11.036 h plus 1.5 of P, that is equal to 0. Okay, so let's move this P here, let's arrange it. So let's put it 1.5 P here on the left. This is equal to, so 11.036 h minus 1.635 h cubed minus 3. Now for P here, that is equal to, so divide all terms with 1.5. So 11.036 divided by 1.5, that is 7.357H minus 1.09 H cubed minus 2. So what is, so 3 divided by 1.5 is 2. So for maximum value, so for max P, dP over dH is equal to 0. So let's derive this. This becomes dP, derivative of P over the derivative of H, and this one is 7.357 minus 3 times 1.09, it's 3.27 H squared minus 0. Okay? Then let's equate this into 0. 7.357 minus 3.27 H squared. So H now is equal to 1.5 meter. Okay? So that's the maximum height. Okay, so that's the height, okay, that will give this pressure or this force here a maximum value. Okay? So it's not necessarily that the higher the value of H, the higher the value of P. Remember that this force here tends to open the gate, whereas this force here tends to close the gate. So the higher the value of this one here, the higher also the value that is the force that is pushing it to open, and also it affects the value of F2 here that tends to close the gate. Okay, so therefore H is equal to 1.5 is the height of the water that will help this force here to be maximum. Okay. So that's for problem 3.26. Okay, so this ends this video.